let's get started with lecture 16. We'll be covering the energy theorems and the theorem of total potential energy. And so we've in the previous lectures, I want to kind of provide the roadmap where we've been. We've been covering some mathematical concepts called the calculus of variations, where I'm trying to find the function that extremizes a functional. And that functional describes could describe a mathematical or physical problem in engineering, or it could be a heat transfer problem, whatever it is. We can formulate a functional that you can then find the function that minimizes or maximizes that functional, and then we apply the idea to the structural mechanics. And in structural mechanics, when I covered that separately, I covered what are the governing equations of elasticity that describe the structural response of a structure when it's subjected to loading environments. And there we covered how we could develop six components of stress and three equations of elasticity that describe the equations of equilibrium, meaning when the loads are applied to the structure is in equilibrium because of these three equations. In addition to that, we then went and developed the kinematics and described why we need to develop the idea of strains, because strains are normalized quantities that tells us how things are straining. Just by looking at a wing deforming 40 feet doesn't tell me a lot about where the structure is going to have a lot of strain. And so that's why we looked at the idea of strain. There are six components of strains, and we developed that. We demonstrated it was symmetric, and we also demonstrated they can be developed by uh, it could be developed by using the idea of kinematics. We discussed the idea of green Lagrange strain tensor, which is for large deformations, and we also discovered that for small gradients, the green Lagrange strain tensor can be uh, summarized or can be simplified to the infinitesimal strains. And from there, we then realized using the idea of incremental work done or principal virtual work, we demonstrated that the stress must be somehow related to the strain. And because of that, we then developed the idea of the constitutive law, meaning that if I have six components of stress and I have six components of strain, something must be relating them. And then from there, I use highly mathematical concepts to demonstrate that there must be a constitutive law that connects the two. And not just that, then I use physical experiments that actually miraculously actually jived very well with the mathematics. That yes, there is a way to connect these six stresses and these six strains through the constitutive law. And so there we had six equations as well, and three deflections, three displacements. As a consequence, we have 15 equations, 15 unknowns that somehow need to be solved over a domain. And that domain can be any domain, like an aircraft, a Navy ship, whatever it is, we have to solve these equations. You cannot solve these equations by hand. I chose the structural concepts because that has the most equations. But I could apply it to fluid mechanics, where pressure and velocity field of the flow is important. You can see here I only have two variables. I could apply it to heat transfer, where I could have temperature as an unknown, and the heat flux are the loads applied. Again, temperature, just one variable. But what is nice about studying structural mechanics is I get 15 variables that are unknown. And not just that, I can now couple structural mechanics with piezoelectric and fluid mechanics and other areas of expertise. And we can then try to solve a multiphysics problem. And in those cases, we're looking at a lot more number of unknowns, and we will then use the idea of trying to solve it using the calculus of variations. So then later on, I stopped talking all about that, about those equations. And then I applied the calculus of variations through the principle of virtual work to derive structural theories. And a miracle happened. When I applied the principle of virtual work to the in and demonstrated the internal virtual work done is equal to the external virtual work done in a very, in my opinion, is a miracle. When you go through all that and use calculus variations, the Euler Lagrange equations happen to be the very equations I had derived using the second Newton's law, or Newton's law in the integral form, which is amazing. Not only that, I was able to come up with a Cauchy's relationship, which I had to use a tetrahedron element before to derive. And then from there, which is that's the most accurate theory you can ever have, I then studied simplifications. I looked at the axial bar. Why did I do that? Because I cannot use 3D theory for everything. Imagine if I model an aircraft and every little strut I model as 3D. That'll be computationally very expensive. What if we try to model it as 1D? That'll be computationally very, very nice. And so that's why I developed the axial bar theory. And that's more like a truss, like something you'll find on the bridge or a strut. Like if you had a launch vehicle design and the launch vehicle design had attachments to components nearby. Say you have a heavy vehicle. Well, the core vehicle is attached to the side cores, maybe using struts that can stretch and compress. That's an example of that. Or bridges, right? So axial bar theory, we applied it to that. We applied some significant assumptions to that that gave us the Euler Lagrange equations for that. And if you go to back to your mechanics materials, you're gonna have a moment of happiness because it's going to match exactly what you learned back in the day. But it didn't really, at the time, they just told you these are the equations. Now I'm telling you where the equations came from. We're also, from there, uh, kind of to showed you there's inconsistencies. Of course, there's inconsistencies. Inconsistencies. Anytime you make assumptions, calculus variation is going to help you figure out, hey, I know you kind of screwed up. I know you came up with assumptions, but guess what? I'm calculus variations. And I'm gonna apply calculus variations to give you the best answer possible, even if you screwed up. Because it is a true screw up. When I make assumptions, it's not perfect, it's incorrect. And if a computer were to look at that, it's going to say that's wrong. But guess what? It's okay. So, it's fine. It's not perfect because engineering is not perfect. Nothing can be perfect. And if you go for perfection, you'll never get it done. And so calculus variation says, yes, I'll take whatever you give me. I'll try to give you the best Euler Lagrange equation for the problem. That's what we did there. And then I went to Euler Bernoulli beam theory, which maybe make back in mechanics of materials. And please, if you haven't taken mechanics of materials, I have a number of lectures in YouTube on static and strength of materials, and I do cover beam theory. Now, over there, we didn't call it Euler Bernoulli beam theory because if you cover that back then, people would be confused. But a beam that's covered in mechanics of materials is simply a beam that can deflect, like a diving board, or something that can bend. And those typically tend to be those that are thin and long. And in mechanics of material, it was given to you the governing equations that basically describe the deflections of that beam. I use principal virtual work based on assumptions of that theory, that initial theory that's put forth to show you what the Euler Lagrange equations are. Again, same situation. The Euler Lagrange equation came by me making assumptions on that theory that the cross section stays perpendicular to neutral axis. I also showed you how other assumptions like no warping, no torsion, and many other simplifications were made, yet Euler Lagrange we were able to come up with the equations that govern the beam, and I showed you how awesome it is to get the boundary conditions automatically. I didn't have to even think about it. Not only that, I know how to cut the structure. If I cut the structures, I know I will have an axial load and a bending load, which is amazing. Back in mechanics of material, we told you that has to be the case, but now it came out. It came out naturally. Then I moved to Timoshenko theory because Euler Bernoulli beam theory is only good for thin and very long structures. But Timoshenko beam theory is very good for thick structures, meaning is the length can be short compared to the thickness. And in fact, we demonstrated that Timoshenko beam theory gives you, again, Euler Lagrange equations, and that theory is more general, the Euler Bernoulli beam theory. And again, there are screw ups again because Timoshenko beam theory tells you that the shear stress through the cross section is constant. We know from mechanics of material it's parabolic. Guess what? That is a consequence of the assumptions we made. But calculus version did the best. It did the best it could. And so now I'm stepping into lecture 16, which is now principle of virtual work is the most general theory you can have. It was true all the way up to the equilibrium equations. When I start to substitute the constitutive law in it, I start to make it more specific, but you could have a nonlinear elastic beam. You can have a nonlinear elastic axial bar. You can have a nonlinear elastic 3D theory or nonlinear elastic Timoshenko theory. But today, I am going to focus in a more a subset. This theory here I'm going to cover today is is more specific than principal virtual work, meaning it's a subset of the principal virtual work, meaning the principal virtual work is a more general theory than what I'm covering today. And I'm going to now, so I'm going to go ahead and now get started with the total potential energy, the idea of total potential energy. The first thing is I want to make sure everybody understands that PVW, I apologize for that. The first thing I want to cover is that PVW is not an energy principle. The principle of virtual work is not an energy principle. And the reason it's not that is an energy principle is because the work done is fictitious. That's why. The total potential energy of the body, the total potential energy of the body is determined from the principle of virtual work. When the internal and external forces are conservative. I'll discuss this a little more, but let's for example look at situations where we have a conservative behavior. So one of the things I want to point out is the total potential energy also comes from when you assume an elastic material. If we assume an elastic material, it can be nonlinear, but in this case, the work of stresses in this deformation process is conservative. So the work of stresses in the deformation process is conservative. I apologize for that. And we demonstrated that an elastic material is one where I apply a load to this structure and it will deform a lot. Say it deforms a lot. But when we remove the load, it comes back undeformed to the very undeformed configuration. That's what an elastic material is. The material can be nonlinear, that's fine, but you can have an elastic material if it's nonlinear anyway. Another point I want to make is what I mean with external forces being conservative. What I mean with the external forces being conservative. What that means is when I apply load P, that load P does not depend on the deflections of that beam, meaning it stays directionally the same, so there's no change to that load. But if I had this situation, and I apply a load here, and it deflects. If that load changes direction because the beam changed deflection, then this right here is a non-conservative load. So a conservative load is one where the load, the magnitude of load, and direction does not depend on the deformation. If it does, then you have a situation that is not a conservative system, and you cannot use the idea I'll be discussing next. So now let's assume now let's look at the strain energy per unit volume. So denote the strain energy per unit volume, and I'm going to denote this as W, small w. Then in that case, we have the following situation. We have that the internal virtual work equals the volume integral of sigma ij as it moves through the virtual strains epsilon ij dv. And this is also this in a deformed configuration. We can write this also in the undeformed volume using the second Euler Kirchhoff stress with the Green-Lagrange strain tensor. And I've already shown you how to relate the left to the right. But I'll focus on the Cauchy stress for now. And I want to point out is that I can write what's inside here as del W dV. I can. So I have now the strain energy per unit volume W, and I have said that sigma ij del epsilon ij is equal to the integral of the volume del W. And so I also want you to notice that if a function W did not exist, it will be very difficult to relate the left-hand side to this expression here. Somehow W has to be a function, an explicit function of epsilon ij for me to be able to go from here, this expression here. I apologize. This expression here to this expression here. That'll be very difficult to do. And so for that reason, I'm going to say that a function W does exist. And I am able to write del W somehow so that W is an explicit function of epsilon so that I can do this. I can do this. I can expand it somehow. If I can do that, if W can be written as a function of epsilon ij, then isn't this sigma ij? And so therefore, I can relate the right-hand side with the left-hand side. I can make that happen. But if W cannot be written in terms of epsilon ij, then you will not be able to make this connection. And you can only write W a function of epsilon ij if you have an elastic material, or a material that when you apply load and the load is removed, it returns to the original state. In other words, the internal work, this internal work right here that we're talking about, the virtual internal work, but this W is internal work, and that work depends on the final and initial states of strain and is independent of the deformation process. In other words, I have a conservative deformation process as a consequence. Okay. Now I can look at the external virtual work. Let's look at the external virtual work. And external virtual work, we've derived that before. And I'm not going to include, in today's lecture, I don't plan to include the inertial load. That's fine. We don't have to do it every time, as long as you know how to tackle it. And so I have this Ti. We've seen this before. And then I have Bi del Ui. Bi is the body forces. Ti are the traction loads applied on the surface. Okay? And I'm going to say, listen, these tractions here and these body forces do not depend at all on the deflections. The magnitude of Bi and Ti are independent. So we're going to say for a conservative loading, the magnitude and the direction does not depend on the displacements. As a consequence of that, then isn't this like a number? Isn't this like maybe equal to 3? I don't know. It's a vector, so I should have written a vector, but it's a number. It's a known quantity. Not a number, but it's a vector. There's a vector and there's a vector. That vector is fully known, and it does not depend on the deflection. As a consequence, what I can do is I can now write del Ti and Ui, because if this does not depend on the deflections, I can bring del outside. It doesn't matter. And then I have plus integral, and you cannot do that in situations where the tractions depend on the deflections. An example you will see later is a beam. And the beam has an applied load P. It's possible then, as you apply that load P, the beam will deflect. If that load P continues to be tangent to that beam, and that's called the Beck's column, then in this situation, clearly the load depended upon what the deflection was here, which means I cannot use this idea of conservative deformation system and conservative loading. I have to stick to principle of virtual work at that point, which is more general, is more correct. So, and the reason you can use this idea right now is because for most 99% of the problems, this is acceptable. And so why not if you can simplify it more? And so because the body forces also are assumed to be conservative loading, I'll put the del in front. So then I get this. Okay. And so what I'm going to do next, I'm going to take this del and put it outside. Very nice. I'm able to remove that del to the outside, which is a big thing that we are able to do. And the second thing I want to point out is that I forgot one step that I can do here that could be very beneficial here. Let me do it here. I can take this del out also. Again, I can only go from left to right if W depends on epsilon ij. If I cannot do that, I cannot go from left to right. I'm stuck on this one on the left. But I can bring del outside again, and if I do that, that's integral v small w dv, and I'm going to call this whole thing u, so I get del u here on the left-hand side. And u here represents the strain energy stored in the body due to the elastic deformation that I have. So del w int internal virtual work equals del U, and U here is the strain energy stored in the body due to an elastic deformation. But you know from the principle of virtual work, we have the idea that the internal virtual work has to be equal to the external virtual work, and I proved that to you. And this type of virtual work principles do exist in heat transfer and other areas of expertise. They do exist. So the internal virtual work equals external virtual work. I'm going to do a little trick, if you don't mind, and I'm going to call this whole thing minus VEXT. I already showed you that this is del U. I already showed you this del minus V external, where V is a potential load. V is a potential load. V is the energy of due to the loads applied or potential loads applied. Okay. Potential energy due to loads applied. I'm sorry, guys. Let me write it down. V is a potential energy due to loads applied. U, and I covered that U is a strain energy stored in the body. And you can calculate the strain energy stored in the body by integrating from 0 to epsilon ij, sigma ij d epsilon ij. Okay, that's how you can calculate U. That's one approach. And so what I can do now, I can bring the right-hand side to the left-hand side and get del U plus V external equals 0. And I'll call this pi. And pi equals U plus V external. And pi depends on UI. Okay. So I've come up with something very interesting. I've come up with the idea that the del, the first version of pi, and pi is a strain energy stored in the body plus the potential energy due to loads applied in the body. If I were to add these together, I get a functional pi. And the first variation of that functional pi, when I set that equal to 0, something interesting really happens. Now you know that when internal virtual work equals external virtual work, the body must be in equilibrium. We covered that. In other words, if the internal virtual work equals external virtual work, then the first ratio pi equal to 0 must also imply that the body is in equilibrium as a consequence. So that takes me to the theorem of total potential energy. And the theorem of total potential energy theorem states of all kinematically admissible displacements those which satisfy the equilibrium equations make or render, I think is a better word, render the total potential energy stationary, meaning del pi is equal to 0 for any del ui admissible field. A very powerful concept. What is this? Let me write down exactly what this means. If I have a beam, a strange looking beam, and I apply loads to this beam, and these loads are conservative, and the material is elastic. It can be nonlinear, it just needs to be elastic, meaning I apply a load, and when you remove the load, it goes back. If I have these two conditions, then what this theorem is really telling me is I can calculate pi, and pi depends on deflections, ui. And that what it's telling us is this pi is going to be equal to the strain energy that's stored in the system plus the potential energy due to the loads applied. And then when I formulate this, when I add u plus v, very interestingly, if I set the first version of pi equal to 0, that any deflections that make this happen render the equations of render the system in equilibrium. In other words, any deflections that are virtual, that are applied virtually to this part, to this piece, to this beam. If I apply virtual deflection to this beam, okay, there will be a set of real deflections that render the total potential energy stationary. Not just that, when that happens, the equations of equilibrium, you're going to achieve the system in equilibrium, and that's described by the equations of equilibrium for that system. Very, very powerful idea that we have in our hands, because now you can finally see for the first time, I can derive now the functional for a system that's a solid body. And now mathematically or physically, just explain it better, if I have this beam with a load applied P, I know what the real solution is. The real solution is going to look something like this, right? We know it's going to look something like that. If the load is conservative, if the material is elastic, I could, maybe this is the real deflection of the body. U of x is a real solution to the problem. But I'll then assume a virtual deflection. And I cannot assume it here because it's clamped. I can assume it everywhere else. That's what kinematically admissible is. I can only change it in somewhere else. What this is telling us is that when I achieve the real solution U, when I find that real solution U, that's the one that minimizes or renders the potential energy, total potential energy stationary. That's the total potential energy right here. TP, total potential energy. Anytime I write TP, that's total potential energy. So anytime I have the deflections that reach the real solution, I have rendered the total potential energy stationary. That's powerful. We can demonstrate through, we can demonstrate by looking at the second variation, and it can be proven that the second variation, when you have a loads, that loads are conservative and the material is elastic, it can be proven that the second variation of pi is always greater than 0. And so pi will always achieve a minimum when the deflections have been found to be the ones that render the system in equilibrium. So anytime we have found the deflections that render the system in equilibrium, pi will have achieved a minimum. A very powerful idea that extends upon what we learned. That extends upon what we learned. Okay, so again, the second version of pi can be shown to be greater than 0. I invite you, if you're watching this video, to go ahead and do it, and share your thoughts on how to go about that. But I do want to cover a little bit how to calculate U for certain situations. So say you have a linear elastic material, so say you have a linear elastic material. For the most general term, for the most general linear elastic material, fully anisotropic with 21 independent constants, sigma j equals Cij KL epsilon KL. The strain energy for this system is 1/2 sigma, or the area under the curve, sigma ij epsilon ij. And so what you want to do, because you have to write pi in terms of U, you have to do that when you use this total potential energy, then you have to write 1/2, and then you're going to have to write it in this way, like that. So U becomes that for 3D body of material, for fully anisotropic case, anisotropic case. Okay, and then you want to write each of these in terms of deflections, and you guys know how to do that. For a isotropic material, the strain energy density, and by the way, I made a mistake. This is small u. That's not big U. To get big U, you have to take the integral over the whole volume of this. Okay. For isotropic material, and we've demonstrated this in one of the problem statements, small u is 1/2, and u here is not deflection, is strain energy density. 1/2 lambda for an isotropic material. This is the formula. And then we know what lambda is for an isotropic material. Okay. So that is the strain energy. And so the total strain energy is the integral of small u dv. Now, that is for a simple linear model. You could have a nonlinear elastic model. That's fine. You can have a completely nonlinear elastic model. But you'll have to do this integral to get a total strain energy. So for example, say the stress example. Let's do a one-dimensional example, a 1D example. So say stress for nonlinear elastic. And I told you stress was E times epsilon to the 1/2, which is going to look a lot like this. So say I want to study some plasticity problem, but it's elastic because when I On load, it comes back. You can still use the theorem of total potential energy because I'm not assuming that there's plasticity. There's no, irreversible damage, right? We're assuming it's fully elastic. Then the area under the curve gives you small u. In this case, is the integral of sigma d epsilon. And here I get integral of e epsilon 1/2 d epsilon, which I believe is going to give you 2/3 e epsilon to the 3/2. I hope. And now you know the strain energy density. So now you have to integrate it over the volume to get the full U, the total strain energy. So that's going to be integral of 2/3 E epsilon to the 3/2 dV. Okay, so that will be the process on how you'll go about for a materials nonlinear elastic. For these ones, obviously it's very clear what the strain energy density is, and you put into the integral there. But if you have this situation where it's a nonlinear elastic material, you can still handle it. It just needs to be completely reversible. With that said, so now let's now revisit Euler Bernoulli beam theory. And let's look at the situation. Let's look at the situation of this beam that's clamped with a load applied P this way. And because you cannot apply point loads to a structure, you can, if you make an assumption, usually you're going to have a 3D structure, say. You can apply tractions. You can apply tractions to a structure. Let's call it P, small p. And let's apply a uniform load Q at the top. And what I want to do is revisit this theory, but I want to include moderate rotations. But small strains. And in fact, let's not apply that end load. Just makes things simpler and keep moving quickly. If you don't mind, we'll just keep moving quickly. Just apply a top load there. Let's just apply the top load there. And let's assume the elastic material is E, modulus E, inertia, moment of inertia is I. Cross-sectional area is A. Okay, so I want to revisit this theory. We talked about the assumptions in this theory. Part 1, assumptions. In this theory, no warping, no torsion, no stretching of that cross section, no, the cross section stays perpendicular to the neutral axis. which means that if this is the one direction, that's the three direction, gamma 1, 3 must be equal to 0. No stretching means that epsilon 3, 3 is equal to epsilon 2, 2 equals 0. And so then I can come up with the deflection assumptions, displacement assumptions for this theory. And I have the deflections in all three directions. And these deflections depend on all three coordinates. And we're going to assume that there's no out-of-plane deflection outside of this page of the board. So that's 0. And I'm going to say that the deflections at every point in that cross-section of this beam, at every point is going to move the same amount. I don't care where it is in that cross-section. That point is going to move the same as any other point. As a consequence, this is small u3, x1. And so it only depends on the axial direction, how much deflection you may have. Okay, because U3 is the transverse deflection. That's a transverse deflection, and this is the axial deflection. For the axial deflection, we're going to say that at every point in the cross section, if I have any type of axial deflection, it's going to move the same as the neutral axis. So that means U small u1 x1. And I'm going to say that the deflection, the axial deflection, depends linearly through the thickness against another variable x1. We demonstrated that gamma 1 3 is the partial of u1 x3 plus partial u3 respect to x1 and partial u1 respect to x3 is theta, and that's u3 prime. So that's 0. So therefore theta is minus u3 prime, and so therefore this is the minus of u3 prime x1. So therefore I get the slope of that beam. So when x3 is 0, you only get axial deflection. And at the extreme fibers of that beam is when you get the highest amount of axial deflection due to the slope change. Very good, very good. Now we can calculate the strains, the non-zero strains. And instead of going through the whole thing again, because I did in the previous lecture, the only one that exists is epsilon 1, 1. The difference is today I'm going to do a Euler-Lagrange, sorry, not the Euler-Lagrange, the Green-Lagrange strain. I'm going to do a larger deformation theory today. So let's look at that. Epsilon 1, 1 is 1/2 partial of u1 respect to x1 plus partial of u1 respect to x1 plus partial of u1 respect to x1, u1 respect to x1. And if somebody can verify that I'm doing this correctly, I'll appreciate it. That I'm writing this term correctly here. Because I'm not following any notes, I'm going by, I'm actually the first time I'm actually deriving this in class, because I can see there's some confusion going on. So can somebody confirm for me that this is correct? And so U2 is definitely 0, so this goes away. And the only thing I'm going to do here is when you bend the beam, it's very unlikely that the gradient of the axial deflection here is going to be that significant. So we're going to assume, you can keep this term if you want. But in today's lecture, we're going to neglect that term, which makes it moderate rotation, small strains. So I'm going to neglect this term, and I'm going to keep this term. So that brings me to the following. It gives me u1 prime plus x minus x3 . U3 double prime plus 1/2 U3 prime but squared. So then now part 4, what I want to do is I want to invoke, before I was invoking the theorem, the principle of virtual work. Today I'm invoking the theorem of total potential energy. So I'm doing a little bit different today. And the theorem of total potential energy tells me come up with a functional pi. That's your total potential energy, which is going to only depend on the deflections. In this case, I only have U1, small U1, and U3. It's a one-dimensional theory because U1 and U3 depend only on X1. That's a good news. And so this is now U plus V external. But for our problem, clearly I'm going to say Q, these are elastic material, I'm going to call it elastic. The load Q, I'm going to say, stays in the same direction, does not depend on deflections. So is equal to triple integral of 1/2 sigma 1, epsilon 1, because the other ones are 0. If epsilon 2 is 0, epsilon 3 is 0, blah, 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 then the only term that survives is this one. And now has the external loads applied that I have to consider. So for the external loads applied, I don't have any body forces, which we could add if we wanted to. No body forces for this example problem. And I only have tractions applied. Oh, and we want to be careful because V external here is a minus. If you look at the definition of how we defined it, and that's done by convention, you can see here we define as a minus here. So I want to be careful how I define that. So I'll put minus here instead. And then the only traction I'm really applying is on this top surface. That's it. That's it. Let me call that top surface S1. And that has differential elements of dx1, dx2. And the traction is applied only vertically down, opposite to the coordinate system, so it's minus Q, which can depend along the length of the beam, times big U3. But big U3 is small U3. Depends only on X1. And you can notice here how none of this stuff, this here does not depend on dx1 or dx2. So I can further expand that a little bit more. Sorry for all the parentheses, makes it very busy. But U3 does not depend on dx1, dx2. So then I have this minus 0, 2. Let's call the length L of that beam. Let's call it L for the first time, if you're okay with that. Times minus Q times B. I integrate through the width of that beam because I can integrate about dx2 there. So I get d u3 x1 dx1, and I'll call qb q bar to make it easier. So now I have q is units of force per inch squared or length squared, and now there's units of force per unit length. So things have simplified further. Sigma 1, 1, I want everything to be written in terms of U1 and U3. I have achieved that so far, except for here. So I have to start doing that. Sigma 1, 1 is E epsilon 1, 1. That'll get me closer to my goal. So then I have pi is equal to triple integral volume E 1, 1 times E 1, 1 divided by 2 dV minus plus now, because this minus sign and that minus sign gives me plus. So that's plus integral 0 to L Q bar U3 x1 dx1. So I want to continue to further expand this, and keep pushing it. So triple integral 1/2 E, and now I know what epsilon 1, 1 is. Epsilon 1, 1 is U1 prime minus x3 U3 double prime, and that's squared. Well, I still have this other term plus 1/2 U3 prime squared, and this is squared dV, and that's pi right now. That's what I get for pi. Now I can continue to make improvements in what I've done, because I could expand this whole thing. And I should do that next. E does not, I'm not going to make E vary through a thickness or across the beam, so let's just take it out of the volume. And I get something interesting. I get U1 prime plus 1/2 U3 prime squared plus x3 squared U3 double prime squared. And then I get a cross term, which is plus 2x3. Basically, I'm just expanding this here. So it's going to be minus okay, that's what I got for pi. And hopefully my derivation is correct, because I really went fast. All I did was use the formula for a plus b squared equals. So that's the formula I used today. That's all I've done there. And so I can now, if I were to integrate this, and this dv here is dx1, dx2, and dx3. If I take the integral of this quantity here through a thickness, which is a dx3 direction, that quantity will go to 0, because when you do that integral, none of this stuff depends on x3. And so the integral of x3 squared, and now I'll do it quickly so you can see. No, not x3 squared, but just x3, will give you x3 squared, which is this is an odd function that will give you even on function, and so that will give you 0 when you do it. So that term does nothing to the total potential energy. In this example, it could matter in another situation. So because it's an odd function. And so I'm left with this. Now, dV is also dA dx1. I want you to notice how none of this stuff, like this right here, does not depend on, like none of that depends on dA, because U1 and U3 only depend on x1, and dA is really dx2, dx3. So that further simplifies everything. And you get 1/2 0 to L E A now, because the integral of dA is A. And you get EA U1 prime plus 1/2 U3 prime squared. And the double integral of x3 squared dA is the moment of inertia. So you get EI U3 double prime squared dx1. And I can bring everything together to the same integral if I wanted to. Okay, this is what we got for pi, and pi depends on two functions, u1 and small u3. Okay, so this theory is really good for large deflections. And now I have developed the total potential energy. Everything is in terms of u1 and u3. And this is an exciting moment, because part 5 is exciting, because part 5 is to find the deflections or displacements u1 of x1, which is a function, right? U1 is a function. And u3, which is also a function. U1 is the actual deflection, u3 is how much it deflects up and down in the x3 direction. So it's exciting because we want to find the deflections u1 and u3 that minimize. We know it's minimized. You're going to show it. The total potential energy. Because we know that those deflections that cause the minimization of pi are the ones that result in the system being in equilibrium. So we're invoking the theorem of total potential energy. And some people call it the minimum total potential energy. We invoke that, which tells us that the system is in equilibrium only if the first version of pi is 0. In other words, if I were to first find the first version of pi and set equal to 0, I can determine the order Lagrange equations. And when I get those order Lagrange equations, the deflections u1, when you solve those order Lagrange equations, you'll find the deflections u1 and u3. By the way, those are the deflections that minimize pi. Those are the deflections that render the system in equilibrium. It's a very powerful idea. And this idea only works when we're looking at conservative deformation processes. Okay? Only when we're looking at conservative deformation processes. It does not work for other scenarios. And I will not do this. I will not take the first version of pi equal to 0 and derive the Euler Lagrange equation. If you're watching in YouTube across the world, or you're taking my class, if you took my class, you got this problem as your exam problem, and you were able to find the first version of pi, set it equal to 0, found the Euler Lagrange equations, showed that the total potential energy is actually minimum at stationarity, which is quite exciting. And those deflections u1 and u3 are the ones that minimize pi that render the system also in equilibrium. And I'll do that in a quick diagram here very quickly. So calculate pi. Invoke the theorem of minimum total potential energy. So find pi and set the first variation of pi equal to 0. Determine the Euler-Lagrange equations using the fundamental lemma of calculus of variations to solve for ui, the deflections. And when you solve for these deflections, those deflections minimize pi. Those deflections render the system in equilibrium. And I'll show you how this idea is powerful. It's not apparent now, but it's a very powerful idea. So I've used a lot of different acronyms here, but we should all be familiar with these acronyms so far. And now what I want to do, I want to step into a second theorem. That's called the first Castigliano's theorem. And what the second and what the first Castigliano theorem says is if I have a body of material and it has some boundary condition somewhere, okay, and I apply a load Q, a particular like a point load Q, and there's a deflection associated with that load Q. It tells us that the total potential energy can be calculated. So you can calculate total potential energy for the system. And I can apply many different loads. That's Q1, Q2. You know, I can apply N loads. And I'm not using index notation here, but I'm going to violate some rules on index notation to make things easier. So the total potential energy, what first Castigliano's theorem says is that the total potential energy must be a function of those deflections that are a consequence of these loads applied. And so that must be equal to the strain energy, the total strain energy, delta I, which depends on the deflections that are applied, minus QK delta K. Or if we don't want to violate the rules of index notation, I'll just write down N loads. And you can see here that this is the strain energy, U, and this right here is the potential energy due to loads applied. And they're being added together to get pi. So what Castigliano theorem said is, hey, the total potential energy is just simply the resulting deflections from load applied. That's all it is. And well, guess what? Now I can invoke the theorem of total potential energy. And when I do that, I find the first version of pi, which is the derivative of pi respect to del And again, I cannot use index notation. I'm kind of stuck because I would like to violate it because I can only go up to 3, but we want to be uh, consistent to what I've taught you. So in this example then, when I set this equal to 0, I find that the derivative of pi respect to delta 1 is the derivative of u1 respect to delta 1 minus q1 delta 1. But for any variations of del delta 1, for any variation of del delta 2, etc., what's in parentheses must be equal to 0 because they're arbitrary variations. And so therefore, the derivative of u respect to, and now I can violate the rule of index notation because I can just say that k equals 1 to n. If I have n laws applied, then Castigliano's theorem allows me to find the strain energy and take the derivative of the strain energy relative to that deflection, and that will give you the force. That's what it's telling us. That's what that's telling us there. Okay, and so that's a very powerful idea that can be used in a lot of different problems. Okay, and I'll show you an example in a second. I want to give an example so you can see how this works. And it's an exciting example. It's actually a very exciting example. I have a truss, and I like it because it's simple, and it shows how this works. And it's pinned here and pinned here. You can probably do it with mechanics materials quickly. Let's consider this bar 1 and bar 2. And I want to apply a load P here. And the question is how much this moves to the right and how much this moves to the bottom, downwards. So if I apply a load P there. And so the first thing that you need to do is calculate. So use first Castigliano Theorem. That's what we want to use in this example. So you calculate the strain energy first, which is triple integral of 1/2. This is a truss system. So only axial load can be taken by this system. And we know that sigma 1,1 is E epsilon 1,1. So that makes everything very quick and simple. And for an axial bar, we know that the other strains are 0. And I don't have any bending, so it's even simpler. I have 2 bars, so I can simplify it even further. We know that epsilon 1,1 does not depend on the cross section, so you can get 0 to L for bar 1. And I'm going to put a coordinate system that goes like that, X, who cares, right? Doesn't matter. And L1 for bar 2. So all I have to do is calculate epsilon 1,1 and for each of these bars, which we can we can do that by geometry. So epsilon 1,1 equals final length minus initial length divided by initial length. That's one way to do it. You can use a full definition of Euler-Lagrange, Green-Lagrange strain tensor if you wanted to, but I don't think it's necessary in this example. This is coordinates at 0, 0, right? So you know where this point is, and you can assume some amount of deflection to the right and to the bottom and come up with come up with how much this strain is for each of the bars. So why we don't go and work through that for a second. And I can do it non-linear. I can actually do large deflection theory if I want to. So epsilon 1 for, and let me call this 0, 0 actually, 0, 0. And let me call this 0h. And let me call this, if it moves an amount downwards to some other point, say it moves down here, is reasonable. It started at HH, but say move that way, amount V. Then this point becomes H plus U, and then H minus V. If this was HH here. So it should be very easy to find the strain in bar 1. Final length minus initial length divided by initial length. And for that, I get 1/2. And I can look at the distance to figure that out. U plus H squared, sorry about that, squared plus V squared minus H. And this is not 2, this is H. So the final length is H for bar 1. I'm looking at this bar here, by the way, the one here. So that makes sense. Is the initial length is H, and the final length is this. By using geometry, it's very easy to find that. But I'm looking at small deflections, so V squared should be close to 0. And so this is going to be approximately equal to U over H. For bar number 2, I apologize for that. And now for bar number 2, which is this one right here, it's the same procedure. In essence, you have to like calculate that final length is literally different. It's 1 over H squared of 2 square root H plus U squared plus V H minus V squared, okay, minus H square root over 2. You can divide everything by H everywhere. So you get 1 over square root of 2. And then you get U divided by H plus 1 squared, 1 minus small v divided by H squared, minus 1. Okay. Hopefully this is correct. I guess I could have left the square root 2 here so you can see what's going on. And you can expand this. When you expand that, you get U naught. Sorry, not U naught. Sorry about that. Trying to make sure we didn't have a mistake. I think this is what we get. And this is very small, and this is very small, so that goes to 0. So then I get this equal And this, after you Taylor series expansion, is approximately equal to U minus V divided by 2H for small deflections. You can keep this large deflections if you want, but then the problem becomes nonlinear. And again, if the strains are less than 1%, 2%, this should be fine. And in fact, you don't want to be designing things that go plastic. It's not a good idea anyway. Maybe some application push you to that, like engine components of a rocket, they go plastic quite a bit. But again, here just use Taylor series expansion, get to the bottom of it, and keep moving forward. So I just calculated strains now. Everything now will be very quickly now in terms of strain energy. So strain energy for this bar system is E over A divided by 2, since the modulus and area do not change as a function of location. And for the second bar, same thing. And guess what now? I can integrate this very easily. None of this depends on the length x. So EA over 2H, when you calculate all this, you get U over H squared plus U minus V 2H squared, square root of 2. When you do the integral, you'll see that's what you get. But we know from Castigliano's theorem first theorem, that if I take the strain energy and take the derivative with respect to the deflection delta I, I'll get the load QI. Well, guess what? Partial of U respect to the deflection U, isn't that exactly 0? Because I'm not applying a load in this direction. At that point, I'm not applying an axial load. So that's 0. And partial of U respect to small v is, now that one, clearly I'm applying a load P downwards with V measured downwards. So therefore that has to be equal to P, and have two equations, two unknowns, and you can solve for U and V. And when you do, you get small u equals the load P applied, H, E over A. You guys can check that at home or use MATLAB. And I get big PH over EA. And I invite you to try to do it with the concepts of mechanics and materials, and I don't think you'll be as successful as we did it here. Like, this is very, very clean. Very, very powerful what we've shown you here. I mean, it's beautiful. I can apply more, I can put more bars if I want. And I can find a deflection of each of those, of that particular point where I'm looking at here, right? So very nice. I showed you in summary in today's lecture, to summarize, I showed you two theorems. The first theorem is a theorem of total potential energy, which states that those deflections that minimize pi are the ones that cause the system to be in equilibrium. And I can do that by finding the first variation of the function of pi. And pi is defined as the strain energy, total strain energy, plus the total potential energy due to load applied. And then now I showed you a new theorem called the first Castigliano theorem, which shows the convenience of this theorem by showing you I can get the deflections by using this simple formula. In other words, if the strain energy can be written as an expression of discrete deflections applied, and I were to take these derivatives, I can actually equate that to the load at that particular point where the deflection was applied. And then that's going to help you then calculate the deflections where you're interested in. With that said, I will conclude today's lecture, and I appreciate your attention today.